Imagine it's your friend's birthday, and he invited you over to his house for his birthday party. You live kinda far away, so you get in your car and you start driving over. As you get near your friend's house, you notice some parking spots. You can tell that the spot closest to you is empty, and it's marked by this green circle, so you could park there. But you don't know if the other spots are empty or taken, so they're marked with a question mark. Now, you've got a tough call to make. Do you grab this empty spot and then walk the rest of the way? Or do you keep driving, hoping to score an even closer spot? You decide it's a bit too far, so you take a gamble and drive on. Once you get to the next spot, you can now see that it's taken. Unfortunately, this road is one way only, so you can't turn around and go back. You have no choice but to keep driving forward. The next few spots are also full, unfortunately. You kind of regret not taking that first spot now. Maybe it was a bad idea to keep driving. But wait a moment, this spot is open. Should you park here? Well, since you're feeling a little lazy, you decide to press your luck and hold out for an even closer spot. But sadly, all of the best parking spots are taken. This is a really epic party, so a lot of people showed up. I bet a lot of people have faced parking dilemmas like this before, although maybe not quite as extreme. But here's a question. Can math help us determine whether to park when you see an empty spot, or to keep driving? Here, you ended up parking far away from your friend's house, but you were very unlucky. You also didn't really have a strategy. Is there a mathematically optimal strategy for parking? Alright, let's make this problem a bit more concrete. You can let this number line represent this road, where your friend's house is at 100 and parking starts to appear at 80. There are parking spots available at integer values along this line, so if you're at an integer value like 82 and you see it's empty, you can park there. But you can't park at a number like 82.4, you have to stick to integer values only. Now, your goal is to minimize the distance between wherever you end up parking and your friend's house. So if you park at 86, this distance is 14. What makes this problem difficult is that you don't know if a parking spot is empty or not until you get there. Only when you drive to 87 will you know that the spot is taken. Combined with the fact that you can't drive backwards means if you pass on an open spot, you can't go back to it. Finally, to solve this problem, you also need to know the probability that a parking spot is taken. This probability gives the chances that the next parking spot is full. If this probability is low, like 25%, then many spots will be open. Then your strategy should turn down open spots more frequently. But if you have a high probability, like 90%, then most spots will be taken. Then your strategy should more heavily consider parking whenever you see an open spot. For this problem, we'll make this interesting and assume this probability is very high at 90%. Can you find the optimal parking strategy? If you like, you can pause here and try to solve it yourself, but if not, just keep watching for the solution. Alright, time to solve this. Intuitively, you should expect to turn down open parking spots more often when you're far away compared to when you're close, but let's try to see why this is mathematically. When you think about it, at an open spot, you just need to weigh the benefits of parking against not parking. So let's do that. If you're at spot 96 and decide to park, then the distance will just be 4. But what distance will we get if we don't park? This is a bit trickier to determine. First, it depends on your strategy, which is what you'll do after you turn down this parking spot. You can have reasonable strategies like park at the next open spot, or reject all spots until 99 and then accept the next open spot. To stupid strategies like park at the next open number that's divisible by 13. We don't care about these stupid strategies. What we want is the distance we'll get from an optimal strategy. In addition, this distance is going to be random. For a strategy like park at the next open spot, where you end up parking is going to depend on which spots are taken, which is going to be different each time. Therefore, the final distance is also going to be random. Since it's random, we can't say for sure that it'll always be bigger or smaller than 4. However, what we can do is take an average for these distances over a large number of trials, and then compare the average to 4. Here, we tried this strategy 6 times, but imagine repeating this a large number of times and then averaging the distances. This average is called the expected value of the distance. In math notation, this expected value is written like this, which assumes we use the optimal strategy starting at spot 97, and we want to compare this value to 4. The tricky part is, we still don't know the optimal strategy. This is what we were trying to figure out in the first place. But there is a way out of this. Although the best strategy is not obvious at spot 97, there is a spot where it is obvious at spot 100. If spot 100 is open, then it's a no-brainer to stop because the distance is 0. But if the spot is taken, then you have to keep driving until you find the next open spot. No matter where the next open spot is, you'll want to park there because otherwise, you'll just end up driving even further away. So, if your car is at 100 or beyond, the optimal strategy is just to park at the very next open spot you see. So, if we know the optimal strategy when we're at 100, what is the expected distance if we follow this strategy? Luckily, it's not too difficult to calculate. At spot 100, there's a 10% chance that the spot is empty, and in that case, we park and the distance we get is 0. But there's also a 90% chance that it's taken, in which case we need to figure out, on average, how many spots we need to examine before we see an open spot. If you're familiar with some probability, you might see that this is the mean of a geometric random variable. But if you don't, it doesn't really matter. Just know that the average number of spots we'll have to see before we stop is going to be 10. All of this equals 9. Therefore, if we're at spot 100 and before we know whether it's empty or not, the expected distance under the optimal policy is going to be 9. So now that we know what to do if we're at 100, let's say we're at spot 99 and it's open. Should we park? If we park, the distance is 1. But if we don't park, we move on to spot 100, and we just calculated that the average distance is 9 if we follow the optimal strategy. Since 1 is less than 9, we should always park at 99 if it's open. If we're at spot 99, and before we see if it's open or not, we can calculate the expected distance in a similar way to before. There's a 10% chance that it's open, in which case we now know we should park, and the distance is 1. Plus a 90% chance it's taken, in which case we move on to spot 100. From here, we can expect an average distance of 9 from the optimal strategy. So overall, this equals 8.2. We can do the same thing for spot 98. If it's open and we park, the distance is 2. If we continue, the expected distance is 8.2, so we should always park. And likewise, we can calculate the expected distance at 98 before we see if it's open, and it's 7.58. We can continue like this and see that for spots 94 onwards, we should always park if we see an open spot. And the expected distance at 94 before we see if it's open is 6.57. It gets really interesting when we move to spot 93, because if it's empty and we park, the distance is 7. But if we continue, the expected distance is 6.57, so we should in fact turn down this open spot and continue. The same thing holds for all of the spots before 93 as well. 94 is the threshold. The optimal policy is to reject all spots before 94, and then stop at the first open spot afterwards. Since we reject all spots before 94, the expected distance of this policy is going to be 6.57, which is the expected distance we'll see if we start at 94 and accept the first spot after. We can also solve this problem when the probability that a spot is full is not at 90%. For example, if it's at 80%, the threshold moves up, because now it's more likely we can get a closer spot. If it's higher at 95%, the threshold moves down, because now it's harder to get a spot, so we want to grab one earlier. This technique we use to solve this problem is called backwards induction, because we first find the optimal strategy at 100, and then use that to find the optimal strategy at 99, and so on. It can also be considered dynamic programming, which is a very powerful technique used everywhere in computer science and optimization. This problem is in an area of math called optimal stopping. It's a fascinating area that deals with problems like this one, where we try to determine the best time to stop. I'll be covering other problems in optimal stopping in future videos. If you enjoyed this video, make sure to like and subscribe for more math modeling videos like this one. Thanks for watching, and see you next time.